Give me a minute. All right, so since it just started recording, let me just repeat what I just said. So when we're talking about the electronegativity of an atom, we are talking about the ability of an atom to attract shared electrons to itself. So the atom that is able to attract the shared electrons to itself, more so than the other one, is said to be more electronegative. And a chemist, a Nobel Prize winning chemist by the name of Linus Pauling, he did some calculations and came up with a table of electronegativity values, which is given in your the table, the packet that I posted in campus. Let me show you what I'm talking about. And I think it's the very last page. Okay, this table right here, this is the table that he came up with, where basically, based on thermodynamic values and so on, he came up with a 4-point scale, right? Where basically 4 is the maximum electronegativity, and then you have other atoms with lower values, right? And basically he came up with this. If you look in different textbooks, you're going to see some slightly different numbers, but we're going to use the values in this particular table, all right? So as you can see from this table, the most electronegative element, according to the scale that he developed, is fluorine, has a maximum value of 4.0, right? And then he has the other values for different elements. And what you'll see, there's some trends that you can observe when it comes to the electronegativity values. One is that they tend to increase as you go from left to right of any period. There are some exceptions, but basically that's a general trend. And then going from top to bottom of any group, the electronegativity tends to decrease. Again, there are some exceptions, but that's a general trend, right? So that's basically what electronegativity is all about. Now, related to that topic of electronegativity is the topic of polarity, right? So polarity is used to refer to the degree of separation of charge that exists within a bond or a molecule, right? So let's talk about the bond first, and then later on we'll get to a discussion of polarity of molecules. Now, what you'll find, as I said before, is that if you have two atoms that are different, bonding to each other, sharing electrons, one will have a great attraction for the shared electrons, right? The more electronegative atom will have a great attraction for the shared electron, right? So, as a result, the electrons that are shared, on average, will spend most of its time around the more electronegative atom, all right? So, a criteria was established to determine whether or not that separation of charge can be considered to be effective, all right? So I'm going to construct a little table here which kind of summarizes the criteria. Let me open this up here. Let me clear this here. All right, so here it is. So in this little table, I'm going to say that here we're going to have the difference in electronegativity values of the atoms involved in the bond and the corresponding bond type, all right? Okay, so let's say you have two atoms that are bonded to each other. And let's say that the difference in electronegativity between those two bonds, between those two atoms, I'm sorry, it lies somewhere between 0.0 to 0.4, right? Then for most intents and purposes, we consider that bond to be a non-polar covalent bond, all right? So in other words, there is a sharing, an even sharing of electrons between two atoms, right? So a good example, let me just create another column here. A good example of this would be the chlorine to chlorine bond, right? These two atoms are identical. That means that the difference in electronegativity between these two will be 0, right? So therefore, what does that mean? That means that the electrons that are shared between those two atoms are shared evenly, right? And therefore, there's no separation of charge, and therefore we consider that bond to be nonpolar covalent. Now, if the difference in electronegativity lies between 0.5 to 1.7, right? Then for most intents and purposes, this bond is considered to be polar covalent, right? So in other words, there's going to be a separation of charge between the atoms. Let me see if I can come up with a good example of this. A good example of this would be the hydrogen to fluorine bond, right? Now, if I were to look up the values, let me go back to the table. Hydrogen is 2.1 and fluorine is 4.0, right? So 2.1, 4.0. What's the difference between these two? What's that? 1.9? Ooh, hold on, that falls outside the range. Let me use a different example. I'm sorry.
That's what will make me confused. I was like, I think it's out. Right.
Use a different example. Okay, let me use carbon to hydrogen. Let's do that one. C to H, right? Now hydrogen is 2.1 and carbon is what? Oh no, that's another bad issue. I'm sorry. I'm messing up. That would be nonpolar actually.
Fluorine and sulfur, right?
Huh?
Fluorine and sulfur, right?
Yeah, okay, let's do fluorine and sulfur, yeah. All right, so fluorine and sulfur. So fluorine is 4.0. What's sulfur?
2.5.
2.5. Okay, that's a good example, right? So the difference in electronegativity between those two is 1.5, which falls within that range. So therefore, the fluorine to sulfur bond, based on this criteria, would be polar covalent. And then the third category, which is the most extreme, is if the difference in electronegativity is more than 1.8, right? So 1.8 or greater, right? If the difference in the electronegativity of the two atoms is 1.8 or greater, then that bond is considered to be ionic. And what that means basically is that the electrons are basically completely transferred from the metal or the more electronegative from the less electronegative atom to the more electronegative atom, right? So a good example of this would be the sodium to chlorine bond, right? Because sodium, let me see here, sodium has a very low value.
Yeah, you could do the hydrogen and fluorine, which will be.
Yeah, we could do that. Let me use this first. 0.9 for this for the sodium, and for the chlorine is 3.0. So the difference is what? 2.1. Right? So therefore the sodium to chlorine bond is ionic. The one that we looked at earlier, which I mistakenly used for the second example. What was it?
Hydrogen, fluorine,
And fluorine, right?
and hydrogen is 2.0.
So hydrogen is 2.1, fluorine is 4.0. The difference is 2.9, so that would be considered to be ionic.
That's 1.9.
I'm sorry, 1.9, yeah. So that would be considered to be ionic based on the criteria here. Let me just say that the criteria is not really a perfect one, but is used, quite a bit in terms of establishing the different types of bonds. So with that said, we can now do the first question in assignment number 12. So let me go here. So basically what they're asking for you to do is to basically determine the type of bond that exists between the two elements given on the left. So basically you're going to use the table with the electronegativity values to determine the difference. So for example, in the case of the first one, okay, for the first one, it's arsenic and sulfur. So arsenic is 2.0. Arsenic is 2.0. And sulfur is 2.5. So the difference in electronegativity would be 2.5 minus 2.0, that would be 0.5. So that would put that in what category?
Polar.
Non-polar, covalent.
Polar.
I'm sorry, polar covalent, sorry. Polar covalent. Non-polar is between 0 and 0.4, right? Okay. And basically, you're going to do the same for the other. So what I want you to do right now, I want you to complete this table. All right. And then after that, we'll move on to the next question. So you're going to need to, in fact, tell you what, let me bring up the table on the screen. This table right here. So you can use that to get your values. Let me clear this here. Right, okay, so I wanted to complete all of that table before we move on to the next question. All right. Sorry.
Uranium is G.
Yes, uranium GE, yeah.
The bottom of the graph that says is that
Lanthanide?
does that just mean for those elements that it can be between 1.1 and 1.3?
Um,
LA.
Yeah, the lanthanides are the elements. There's a special block for them. I think they call the F block elements that would fit into where this is. But they're hold on, let me see here. Usually in most periodic tables, here it is right here. In most periodic tables, after the lanthanides, they put a special block outside of the rest of the table, which starts with the next element after lanthanum, and they have all these here. So these elements here in this block here would fit into where you have the lanthanide right here.
Okay.
Right, but apparently, I suspect that they have some difficulty determining the electronegativity values on those elements, so that's why they just put 1.1 to 1.3.
Well, I noticed on the last paper, thing we were doing the assignment, wasn't there two elements that technically, like in chemistry, one or two, that like writing these out,
Oh, okay,
technically, and is it the MO, I think? That's technically, um. 4D is technically 4, and then the one goes here to balance it out. Chem
yeah,
one,
right, so, I mean, assuming
Chem
that,
1 and Chem 2, whichever one.
right, hold on, let me see here. So this is what you have in for these?
Yeah, 44,
Okay,
because
so that
technically the proper is
You should have,
45. and
exactly,
that's one,
exactly, exactly.
But we don't get into that till Chem 1 and Chem 2.
Right, exactly, yeah, yeah, so I would accept that as it is. Did everybody sign the attendance sheet? All right.
I just like to look into that stuff because it's same as like math where, they'll say, oh,
Yeah,
do it this way, but then when you actually get into it, it's not proper.
yeah, things are a bit more complicated. That's how things are, the higher you go.
That's it.
Yeah.
That's.
Okay, are we finished? All right. So let's continue with the next question. All right, so the next question is asking for you to draw the Lewis structures for the following and give the geometry in each case. All right. Now I'm trying to remember, did we get into a discussion of drawing Lewis structure? I think we did some from the PowerPoints.
Oh, yes.
Right, okay. So basically it's the same steps that you're gonna follow in order to answer these questions. So let's start off by looking at the first one. But now we're going to get into, in addition to the Lewis structures, we're going to get into the geometry. Which I think we discussed as well. No, did we? Maybe not. I'll get to that. But that was covered in the videos as well. So let me deal with the Lewis structure first. So you're given NOCl. So the first step to getting the Lewis structures is that we count up the number of valence electrons contributed by each element, by each atom. So we go to the periodic table and we look up the group number for nitrogen, it's 5. We look up the same for oxygen, that's 6. And we look up the same for chlorine, and that's 7. So we add these up, 5 plus 6 gives 11 plus 1, 18. I'm sorry, plus 7, 18. So 18 electrons, and I like to express them as pairs. So that will be 9 pairs of electrons, right? So we put the most, or I should say the least electronegative element in the center, which, if I'm not mistaken, will be nitrogen. Let me just check the electronegative values here. Nitrogen is 3.0, oxygen is 3.5, chlorine is, okay. So it's a toss up between nitrogen and chlorine in terms of which one is placed in the center. I'm going to put the nitrogen in the center, all right? So nitrogen in the middle, surrounded by the chlorine and the oxygen. And then what we're going to do first is put the bonding pairs first. So we have 9 pairs to play with. 1, 2, the first 2 pairs go between the oxygen and the nitrogen and chlorine. And then 3, 4, 5, 6, 7, 8. All right. Now, for most of these molecules, we try to ensure that each atom has an octet, 8 electrons on its outer shell. Now, that's true for the oxygen here. This oxygen has 2, 4, 6, 8 electrons. And that is also true for the chlorine here. 2, 4, 6, 8 electrons. But that is not true for the nitrogen here, right? In the case of the nitrogen, it has only 2 pairs or 4 electrons, right? So how do we end up with 8 electrons for the nitrogen? Well, what we can do is, hold on, did I make a mistake here? 1, 2, 3, 4, 5, 6, 7. Oh, there's one more pair I need to add. I'm sorry. So far, we have assigned 8 electron pairs, but there's one more pair, because we're starting off with 9 electrons. So therefore, we put that pair on the central atom right here. All right. So now, go back to what I just said. Each atom, we try to have them ending up with 8 electrons on their outer shell. That is true for the nitrogen. That is true for the chlorine. But that is not true for the that is true for the oxygen. That is true for the chlorine. But that is not true for the nitrogen, because in the case of nitrogen, as you can see here, you have 2, 4, 6, or 3 pairs, right? So the question now becomes, how do we end up with 8 pairs of electrons on the nitrogen atom? And basically what we can do is push this pair of electrons here to form another bond right here, and therefore the final structure would be this. And that's it. So now every atom has 8 electrons on its outer shell. The oxygen has 8, the nitrogen has 8, and the chlorine has 8. So this would be the Lewis structure for this molecule. All right. Now we're not finished yet, because we need to find the geometry, right? Now the geometry is when they're talking about the geometry, they're talking about the shape of the molecule, right? And the shape of the molecule is based on the electron arrangement around the central atom. And I want to pull up a chart here, which you will have access to. So let's go. Let me go here. Close up. So what I'm about to show you is based on a theory which is known as the valence shell electron pair repulsion theory. If I can find that dark chart. Where is it? Oh, it's in this folder. And basically, oh, here it is. Okay. So basically what this theory says is that if you have a molecule where you have a central atom, right? And the central atom is bonded to other atoms and also has lone pairs. The shape of the molecule resulting is going to be due to the repulsion between pairs of electrons bonding and lone pairs around the central atom, all right? So this chart here basically summarizes the shapes that you're going to end up with based on that theory, all right? So the simplest one, which is this one right here, is the linear shape. This is where you have a central atom. E represents the central atom, and X represents the atoms bonded to the central atom. So basically, in the case of this arrangement here, where you have the central atom bonded to two other atoms, because these pairs of electrons will repel each other to be as far from each other as possible, the most stable arrangement is going to be what we call a linear arrangement, where the bond angle around the central atom is 180 degrees, right? So any molecule where you have that situation, where you have the central atom bonded to two other atoms, right? Then basically, because the bonds will be pushing each other away from each other, the most stable arrangement would be the linear arrangement, which is 180 degrees, right? So that's what happens. So an example, I can give you a couple of examples of this. One example of this would be one example of this would be carbon dioxide. This is the structure of carbon dioxide, right? So basically, you have two bonds here and here, right? They will repel each other to be as far apart from each other, and therefore the shape of the carbon dioxide molecule is going to be a linear shape. You can literally draw a line from one end of the molecule, oxygen, through carbon to the other oxygen atom, right? So that will be the shape of the carbon dioxide molecule, all right? And then now to get to more complex examples, in the case of a central atom bonded to three other atoms, the shape of that molecule would be trigonal planar, and again, it's based on the VSEPR theory, where the bonds will spread out, repel each other to be as far from each other as possible. Now, if you look at this structure here, when you compare this structure to this structure, the only difference between them is that where you have a bond here connecting the atom, the central atom to X, here you're going to have just a lone pair. So there's no other atom here, right? So this lone pair will occupy the same position as this right here. However, the shape of the molecule is determined by the arrangement of the atoms. So in this case, the arrangement of the atoms is what you see here. The E bonded to the two X atoms here. The bond angle would still be approximately 120 degrees, but the shape now is called bent or angular. All right? So that's what happens in the case where you have a central atom bonded to two other atoms, and there's a lone pair of electrons on the central atom. And we can continue to look at the others. In fact, let me clear this here, even though I'm going to need this to answer the first question. So you can look at the others here, and basically based on the arrangements, in terms of bonding pairs and bonds, you can determine the shape of the molecule. So just to pick an arbitrary example, if I were to end up with a molecule with this arrangement, where you have the central atom bonded to four other atoms, but that central atom has two lone pairs, the shape of that structure will be square planar, right? So that's how you can use this as a guide for making predictions as to molecular shapes. Now, going back to the question, Let me see if I can retrieve. Okay, good.
With the one on the, yeah. The one on the bottom.
Okay, good, right. Okay, so in this particular case, I wish I could, you know what, let me try this. We'll try to do something of a split screen kind of situation. Shoot that over. Okay, okay, so in the case of determining the geometry for this molecule, right? Basically, you have the central atom here. That would be your E. Right? That would be your E. Your E will have a lone pair of electrons on it right here, and then that would be bonded to two other atoms. One is X, and I'm going to call both of these X. Right? So basically, we have two bonds, and we have a lone pair. So if you consult the chart, which is what I was hoping to be able to share on the same screen. So if you consult the chart, oh, okay. Okay, so this is the chart right here. So the structure that is similar to what I just mentioned. The central atom bonded to two other atoms, and you have a lone pair would be this one right here, right? So therefore, we can go back to this and say that the molecule would be of a bent geometry. Let me see if I can retrieve this thing here again. Okay, so therefore, if you have a lone pair on the central atom, and the central atom is bonded to two other atoms, as you can see here, we can say that the shape would be bent or angular. So I'm going to put bent here as the answer for the geometry. Right? Now, the next part of the question is asking for whether or not the molecule is polar. All right? Now, let's go back to what we said about polarity of bonds. Remember, we said that when a bond is polar, right? One atom will have a greater attraction for the shared electrons compared to the other atom. As a result, the electrons that are shared will spend most of its time around the more electronegative atom. So that bond is polar, right? And let me give a quick example here just to explain further. So here's here. Okay, so if you have, let's say, a hydrogen bonded to a hydrogen, right? We know that this bond is non-polar, okay, because both atoms are the same, right? But if you have a hydrogen bonded to a chlorine, then we know that this bond is polar, all right? And the way we indicate the polarity is that we draw an arrow in this direction. Now, the reason why it's going in this direction is because the electrons here will be shifted towards the chlorine. The chlorine is going to have a partial negative charge, and the hydrogen will have a partial plus charge, right? So we say that the direction of the polarity of that bond would be from the hydrogen to the chlorine, all right? Now, if you have carbon dioxide, right? Let's look at this molecule here. Oxygen is more electronegative than carbon, right? So for this bond here, the dipole or the polarity will be acting in that direction. For this bond, the polarity will be acting in that direction. All right? So what we have is a situation where the bond, or I should say firstly, the molecule is linear, right? you have one dipole acting in this direction here, the other dipole will be acting in this direction, right? And because this oxygen is identical to this oxygen, that means that this dipole would be equal in magnitude but opposite in direction. So what does that mean? That means that they will cancel out each other. So therefore, the net polarity is equal to 0 because the dipoles cancel out each other, and therefore we can conclude that the molecule is non-polar. The molecule is non-polar, all right? So if you have different polarities in a molecule, but they cancel out each other exactly, then we can say that the molecule is non-polar, all right? Now let me just say this as well. Let's say I were to replace this oxygen with a different atom. Let's say I replace it with a sulfur atom. All right? Now, because the sulfur here is different from the oxygen, right? What that means is that this polarity here will be different from this one. And what that means, therefore, is that they won't cancel out each other. And if they don't cancel out each other, that means that the net polarity would be a non-zero value, right? Which means that the molecule would be polar. All right? So basically, if you have different bonds in a molecule and they don't cancel out each other, right? Even if it's symmetrical, if they don't cancel out each other, then the net polarity of the molecule would be a non-zero value, and therefore the molecule would be considered to be polar. All right? Let me give another example before we answer the question here, because I think it's important that you get a good grasp of what we mean by the polarity of a molecule. So let me clear all of this here. So let's say you're given carbon tetrachloride, which has this formula, CCl4, right? And let's say you go through all the steps to determine the Lewis structure, and basically this is what you end up with. Right? So the next thing we need to determine is the shape. So you go to the table that I showed you earlier. Right? So which structure here corresponds to carbon tetrachloride? And that is this one right here, where the central atom is bonded to 4 other atoms, right? The shape of that molecule will be tetrahedral. Okay? So in the case of a tetrahedral molecule, so let me just write out here, this will be tetrahedral. Now, I'm going to represent this in a more three-dimensional way. Okay, so this is just another way of representing the tetrahedral shape. For those of you who have to do organic chemistry, you're going to see this a lot, all right? This wedge-shaped bond right here represents the bond that is sticking out of the plane of the screen, and this bond here with these lines, these parallel lines right here, represents a bond that is sticking behind the plane of the screen, right? So if all these atoms are identical, you're going to have one dipole acting in that direction, the same magnitude dipole acting in this direction, the same magnitude dipole acting this direction, and in this direction, right? Basically, if you think about it, and you may have to use your imagination to think about this in a three-dimensional way, right? What you're going to see is that those dipoles will cancel out each other, right? So therefore, the net polarity would be equal to 0 because they'll all cancel out each other, which means that this would be a non-polar molecule. All right? So again, this is an example where even though you will have polar bonds, but because of the symmetrical distribution, spatially speaking, they will cancel out each other, and therefore the net result is that the molecule will be non-polar. All right? Okay, I think I've said enough here for us to look back at the question. Okay, so okay, so this is the Lewis structure here. This is the representation here. It's bent. So therefore, if it's bent, it's going to look something like this. N Cl double bond O, right? So basically, this dipole will be acting, let me see here. Oxygen is more polar than nitrogen, so therefore you're going to have this dipole acting in that direction. Now, nitrogen is more polar than chlorine, I think, so therefore you're going to have this dipole acting in that direction, right? So therefore, these dipoles will not cancel out each other. So therefore, as a result, the molecule is going to be polar because the net polarity is a non-zero value. All right, the net polarity will be non-zero, all right? And that's basically it for question number one. Any question about it? Any questions? Any questions? Okay, let me clear this here. And let's look at the next one. So the next one is COCl2. So firstly, we need to draw the Lewis structure. So we go to the periodic table and we look up the group numbers for each of these. For carbon, the group number is 4. So it's going to contribute 4 valence electrons. For oxygen, its group number is 6. And for chlorine, the group number is 7. But because we have 2 of them, we have to multiply this by 2. So for the chlorine, total will be 14. And then we add this up. So 6 and 4, 10 plus 14, that's 24 electrons, which will be equal to 12 pairs. Right? So we start off with carbon in the middle, and we surround it with the oxygens and the chlorines. And then we put the bonding pairs first. So we have 12 pairs. The first pair goes here, second pair goes here, third pair go here. Then 4, 5, 6, 7, 8, 9, 10, 11, 12. All right? And then now we recognize that chlorine has 8 electrons here and here. Oxygen has 8 electrons. Excuse me. But carbon has 6 electrons. So carbon needs to get an octet. So the question is, how do we end up with an octet for the oxygen? We can move this pair of electrons down here, and you're going to end up with this resulting structure. All right. So this would be the Lewis structure for this molecule. All right. Now, the next question is the shape. Right. So we have to go back to the table here. All right. So we have to ask ourselves, where can I fit this? Okay. We have to ask ourselves which of the structures that we have in the table fits this arrangement where we have a central atom bonded to 3 other atoms and no lone pairs on the central atom. And the one that fits this, the one that fits this arrangement here would be this right here. Central atom bonded to 3 other atoms, right? So the shape here would be trigonoplanar. So I'm going to write here, trigonoplanar shape. All right. And then the next question is this molecule polar? Well, let's draw the trigonoplanar shape for this here. It's going to be this. C double bond O. And then you have chlorine here and chlorine here, right? Now, you're going to have a dipole acting in this direction here. You're going to have one acting in that direction here and one acting in that direction here, right? But here's the thing. Oxygen is different from the 2 chlorines, right? So you don't expect this to be of the same magnitude as this or this. So therefore, as a result, they won't cancel out each other, right? Because you have 3 different atoms here. So therefore, you'd expect the molecule to have a net polarity, which is a non-zero value. which means that the molecule is polar. All right, so the molecule represented by this formula would have a net polarity, and therefore the molecule is polar. All right, and that answers number 2. Any questions about that? Any questions? Okay, let me clear this. Now, let's see if we can do number 3 with minimum help from yours truly. So, what's the first step in this process?
You probably remember sulfur. Yeah.
Okay, so sulfur will contribute how many valence electrons?
6.
6. And fluorine will contribute how many?
14.
14. 7 times 2 equals 14 electrons, right? So we add this up and we get a grand total of 20 electrons, which will equal to 10 pairs. Okay, very good. What next?
Sulfur will be
Sulfur in the middle, surrounded with the fluorines. And then what?
pair between both forms.
Okay, very good. Bonding pairs first. Then 3, 4, 5, 6, 7, 8, 9, 10. All right, okay. So based on this, what will be the shape of the molecule? So now you have to refer to the chart. See if I can bring it up here. Okay, so this is the chart right here. So which one of these would fit the arrangement? Now remember, the arrangement here is that you have a central atom bonded to 2 other atoms, and you have 2 lone pairs, right? So which one of these would fit, put this like this. Which one of these structures here would fit this arrangement? No, because linear has 2 bonds but no lone pairs. This has 2 bonds for the central atom and 2 lone pairs.
Would it be angular?
Would be angular, which one? There are 2, there's
The 109 degree. Wait,
exactly this one right here.
yeah,
Because this central atom is bonded to 2 atoms and has 2 lone pairs, which is the same arrangement here. So that means that the shape would be angular or V-shaped. All right, which means that it's going to look like this: fluorine, fluorine. So based on that, what do you think the polarity is going to be? It's going to be polar because you're going to have one dipole acting in this direction, another dipole acting in this direction. So they will not cancel out each other, right? So therefore, the net polarity would be a non-zero value. So therefore, the molecule will be polar. All right? Any questions about this one? Okay, let's look at number 4. Let me clear this here. The carbonate ion. Okay, so tell me what to write down. What are the steps?
Valence electrons for carbon.
Okay, carbon is what?
Carbon is 4.
Okay, good. Oxygen is what?
8.
18, 6 times 3, 18. Now, I don't remember if I told you about this here. If you have a negative charge, you need to add an electron for each negative charge. All right, to the total that you have added already, right? So in this case here, you have 2 negative charges, right? So therefore, we need to add 2 more electrons to the total. So that would be 20 plus 4, 24 electrons, which would be equal to 12 pairs, all right? Okay, what's the next step? Now that we know the number of electron pairs that we need to be working with, what's the next step?
You put a carbon.
Carbon in the middle and surrounded with the
Yeah.
oxygens, all right? And then what?
Pairs of 2 oxygens.
Bonding pairs, 1, 2, 3. What next? But the non-bonding pairs, so 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've used up all 12 pairs. Okay, and what next? What do you think is gonna happen next? You're gonna need a double bond because the carbon has 6 electrons and it's going to try to get 8, right? So basically we can shift a pair of electrons down here. So you're gonna end up with C, double bond O, single bond O, single bond O, and that would be the Lewis structure. And then because you have a -2 charge overall, what you should do is put this in square parentheses, like this, and put 2 minus outside, just to indicate that the total charge is -2. Next step is to determine the what? Geometry, okay. So to determine the geometry, we look at the arrangement here. Here, we have a central atom bonded to 3 other atoms. So let's see which one of these structures here would fit that arrangement. Okay, so central atom bonded to 3 other atoms. Which one of these would fit that arrangement?
Right.
This one right here. Central atom bonded to 3 other atoms. And let me just say this, I don't think I've said this before. It doesn't matter if you have double bonds or triple bonds, right? You're not concerned about that, right? Basically, you're just concerned about the atoms bonded to each other in order for you to determine the shape. So therefore, as he correctly said, the shape would be trigonal, oops. Yeah, trigonal planar. All right. So if the shape is trigonal planar, then what would you expect the polarity of the molecule to be? You sure about that? Trigonal planar is this right here. Right? These atoms are identical. So this is a perfectly symmetrical shape where the bond angles are 120 degrees. So if it is symmetrical, that means that this polarity here will be acting in this direction. And so on and so forth. So it's a symmetrical distribution of the polar bonds. So therefore they'll cancel out each other. So therefore the net polarity is equal to 0, and therefore the molecule will be non-polar. And that's it. Any questions? Okay. Number 5. Okay, let me clear number 4 first. Excuse me. Number 5 is ammonium. So let's go through the steps again in this case. So the first step would be what's the first step?
N equals 5
Okay.
and H equals 4.
Okay, 4 times 1. And you have a plus charge,
Yeah.
which means that we do 1. What do you think?
Take away 1.
-1, exactly. So that's 5 plus 4, 9 plus -1, so that's 8 electrons, which will equal to 4 pairs, right? So we put the nitrogen in the middle, and so surrounded with the hydrogens. And then we put the bonding pairs, 1, 2, 3, 4, and that's it. In this case, we put parentheses around it, and we put a plus charge, just to indicate that the entire structure carries a plus charge. Okay, so what do you think the next step is? Hmm? Okay, so we have a central atom bonded to 4 other atoms. So what geometry that would correspond to? Here's the chart. Which structure corresponds to a central atom bonded to 4 other atoms? Tetrahedral is indeed correct. All right. So therefore, tetrahedral is a geometry And therefore, the next question is the polarity. Would you expect this molecule to be polar or non-polar? Non-polar would be correct. So, non-polar would be the geometry, would be the polarity. I'm sorry. All right. And that's it for that one. All right. Any question about this? Any questions? Okay, let's look at number 6. Whoops, let me clear this here. CF3 plus. Okay, so first step.
C equals 4.
Okay, that will contribute 4. What about the fluorines?
That's 7 times 3.
7 times 3, which is 21. And the plus charge?
Minus 1.
Minus 1, so that would be 24 electrons, which is 12 pairs. So we put the carbon in the middle, surrounded with the fluorines. And then we put the bonding pairs first. 1, 2, 3. Then the non-bonding pairs 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, what's the next step? Form a double bond because the carbon has 6 electrons on its outer shell. So it doesn't matter which one of these contributes up here. I'm just going to put these here. So the structure would be fluorine, single bond, double bond, F, single bond, F, and then we put a plus charge around it. Okay, next step. Now that we have the Lewis structure, we need the geometry. So in this case, we have a central atom bonded to 3 other atoms. So which one of these
Trigonal there.
trigonal planar? Exactly. So, trigonal planar. Okay, and what would be the polarity? Non-polar, exactly. And that's it, all right? Okay, very good, all right. Any questions about this one? Any questions? All right, let me clear this. Oh, there's another one, I thought this was it.
2.
2 more, okay. Let's do PDR3, all right, so first step,
Well, close.
he will contribute how many?
1.
5, all right? And bromine will contribute how many? 21, so that's 7 times 3. 21, right? So we add these up, we're going to get 26 electrons, which will be equal to 30 pairs, all right? So we put the phosphorus in the middle, surrounded with the bromines. And then we put the bonding pairs. 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12, which means that the 13th pair would go on the phosphorus, all right? What next?
You agree with Eric?
No, because phosphorus has 8 electrons already, so it doesn't need, right? You only do that if the central atom is deficient in terms of not having 8 electrons, all right? But the phosphorus in the middle already has 8, so we don't need to do that. What's the next step? The geometry. So here we have a central atom bonded to 3 other atoms and a lone pair. So let me bring up that chart again. So which one of these fit that arrangement?
Trigonal pyramid.
Exactly. That will be this one right here. So the shape or the geometry will be trigonal
Pyramid.
pyramid. And the next question is the polarity. Non-polar. No, actually polar. Because
The electron doesn't pull the same.
this is the shape here. This is the 3-dimensional shape. Right? You're going to have which one is more polar? Hold on. Which one is more? I think the bromine is more electronegative, but I want to confirm that. Okay, so phosphorus is 2.1 and bromine is 2.8. Okay, so bromine is more electronegative. So therefore, the polarity direction would be this direction here, this direction here, this direction here. So obviously they won't cancel out each other, right? So therefore, the polarity of this molecule is polar. All right, and that's it. Okay. Any question about this one? All right, the last one. Here it is. Is nitrate. Okay, so first step is on the valence electron. So nitrogen is how many? 5, and oxygen is 6 times 3, 18. And the negative charge will contribute how many? 1. Okay, so that's 24 electrons equal to 12 pairs. With the nitrogen in the middle, surrounded with the oxygens. Bonding pairs 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. And in this case, what's going to happen next?
You put the brackets around it.
Because the nitrogen has 6 electrons, it needs another pair. So therefore, this would be the structure resulting. N double bond O, 2 lone pairs, single bond O. And then we put that in square parentheses and put the negative charge outside, right? Okay. So that is a Lewis structure. So what would be the shape of this structure here? Trigonal, planar, right? And what would be the polarity? Non-polar. Because trigonal planar, that would be totally symmetrical in terms of the spacing. And the dipoles will cancel out each other. Okay, so that's it for this assignment. So what I'm going to do now is open up a Dropbox for this assignment. Here it is. Okay, so this is assignment number. Assignment number is 12. And here. Okay, so I'm going to let this video on the 23rd. Okay, so it's now available, so make sure that you complete it and submit it in that particular Dropbox by then. Let's see something here. Okay, so the next chapter will be chapter 14, and that will be the last chapter. So what I'm going to do is I'm going to open up I'm going to publish the videos for that one, and that's going to be it for the course. Unfortunately, I won't be able to do chapter 15. I wish we could, but. Okay,
Can you publish the chapter 15 video?
well, yeah, I could publish it, but we won't,
Just so I can.
yeah. It's kind of important actually, that chapter.
I gotta go to Chem once. I think Chem need it.
Yeah, because you're gonna need, yeah, some of this in Chem 1. So I'll leave it open for you to watch it if you want to watch it, but
Thank you.
for next class, we're going to discuss chapter 14, so make sure you watch those videos. It's not long, only 3 links, so shouldn't be a long watch. And come next class, we'll discuss problems associated with that. All right, and I should be finished with your test number 2 in terms of grading it, so look out for your grade. If not this evening, definitely by 4. All right, you too.
School business, all close, customer shop, I wanna make sure it's.
The lowest test score of the job, and I will drop the lowest 3 assignment scores.
I don't see that.
What's that?
Yeah, I saw that the weeks ago, I'm like, oh.
I don't worry, you guys took the syllabus again, and I didn't see that at all.
Yeah.
It's like right by the test.
I was wondering, because my college algebra teacher, I brought that up to her, that was like, I think I got a 20 last test. And I'm good at guessing.
Alright.
Like for college algebra, I think dead on the mark for every test she's done. And like, yeah, I think I got 20. I was originally thinking I was gonna get a 96 based off the past 2 years test.
Uh-huh.
But then when I actually got the test, I was like, oh, it's a 20. I had a question.
Yes, sir.
So I might have just misunderstood. What is determining like why we're putting them in the center?
Oh, least electronegative element is the one that's placed in the center.
Okay.
But there's some exceptions. In that, well, firstly, hydrogen is always not in the center. Because hydrogen can only form 1 bond, right? So normally it would be the least electronegative element that's placed in the center. But in something like water, even though oxygen is more electronegative than hydrogen, oxygen is placed in the center because hydrogen cannot be in the center.
That's
Exactly.
why H is on the 2.
Right.
So that's an easy way to remember that.
Right.
It's-
The least
make sure to think about that.
Yeah, exactly. But generally speaking, it's the least electronegative element that is placed in the center in most cases.
This is actually. Like, I'm really liking this stuff.
Oh, you know the structure?
Yeah.
That's kind of important in terms of, and that's why I wish we could get to chapter 15, because that's where you're gonna see how the structure affects the properties like solubilities and boiling points and melting points and all that good stuff. So unfortunately, we won't get into it, but if you do Chem 1, then you should get into that
Yeah,
when you get to that stage.
Chem 1, you teach that in the fall.
I teach Chem 1 in the fall, yeah.
Okay. Cause my plan was, what I'm gonna do is, over the summer. Is, do the modern states for Chem 1, but not test out of it, just do it.
Oh, okay.
So then I kind of pre-learn. And, cause that's what I'm gonna do for the pre-calc and trig also.
Oh, okay.
And I actually bought old books for pre-calc and trig, just so I can kind of, get prepared for it. Don't know what my schedule's gonna be after that though, cause, what they want me to do after that is kind of nonsense. Like for scheduling wise, at least. I think it's crazy, they want me to do, I think they want me to do Chem 2 with Calc 3 and Physics 2. Yeah. I'm like, okay, yeah, you guys are funny.
Hold on. You guys out there in Zoom, I'm signing off now.